structure like this is very complicated looking. Here I'm plotting, because you now think about in three-dimensional space, right? And you try to plot three-dimensional space in some way, right? So here I have, this is my three-dimensional object, and I'm trying to plot them into a two-dimensional page, and this becomes tricky. So what people do is that they, in the Brillouin, right, they identify the symmetry line and critical point. So these special points are called critical point in the Brillouin zone, and these are critical features. So the line is corresponding critical features is a delta, for example, corresponds going from this point to this point. And this way, just to indicate direction, direction in K-space, so that people know which direction you're talking about. So now once you identify the direction, let's say I'm plotting from tau, right, tau to x, this line from here to here. So that defines my K direction, right? Then what do? Once I define my K direction, I can then slice it. I can slice my Brillouin on my band structure, make a slice like this, right? Let's say make a slice like this, cross section across, and then take out my energy level, and it look like this. Okay, so that draw show me how the energy changes along this slice, along this direction, right? So this is how people show, because it's almost impossible to generate a curve like this unless you do it surface by surface. But from an experimental point of view, it's not so practical because you don't know which surface belongs to which because they tend to be intermingled with each other. So what you can do is that you can say, okay, I'm going along this direction, and then I try to measure the energy, and this is what I see, right? This kind of band structure is what you see. And I can change direction. I can change from let's say, going from tau to m, this critical point, going this way, and I got tau to m is this way, or m to tau, going this way. So you see this. So by cutting slices on this whole structure, you can reconstruct, hopefully, at least you can, if you do enough slice, you can imagine you can reconstruct the entire surface, the entire band structure that you see. Okay, so you need symmetry point and you have critical point that help you draw or plot, display the information you need. So if you look at this right away, you notice that, okay, without knowing anything, I know that this is for free electron only. Why? Because there's no gap. Okay, there's no gap because this kind of look like my parabola, for free electron. E is equal to proportional K squared, right? So I don't see any gap. And free electron, you don't see gap. Why you don't see gap? Because there's no boundary condition, right? No boundary condition. And so because there's no boundary condition, there's no restriction. The boundary condition create quantization, right? So no boundary condition, no quantization. Your energy can take on a continuous value as you go through. If you have quantization, you have boundary condition, it creates quantization where you quantize where you cannot have a free choice of your energy level. So here I have quantization. You can see that this gap created, this must be for a real surface because I'm not looking for free electron anymore. This must be for electron that actual real electron in a square lattice, and it generates this gap. And these gaps, some of these gaps can now be called band gap because depending on how many electrons you have, you fill out this gap, right? You fill out this gap according to the density of state, right? Your density of state tell you the number of energy level you got. You fill them up and up to the maximum, and that will be the top of your valence band. And then the next, there usually is a gap between the top of the valence band to the conduction band, the empty band up here, which has its own density of state, right? So these kind of thing would be the band. So most likely, would be this one. That could be the band gap, depending on what material you're talking about, how many electrons. Okay. So from here you can get a sense of the Brillouin zone and the electronic band structure of solid. You need these critical point to identify the direction of the band, the slide you're talking about in 3 dimensions. And it could get quite involved, quite complicated. So here is a two shape of your Brillouin zone, of the first Brillouin zone, what it looks like, the boundary of your Brillouin zone. And so FCC and BCC, body center cubic, and base center cubic. And here you have the standard point that people define, sigma, d, and so forth. And usually, one thing is for sure, that the zone center, the origin of any Brillouin zone, is always capital, called lambda, or tau, maybe tau. This is a symbol like this. It's always correspond to the zone center, and 100 direction, depending on which crystal structure you have. You could have it could be called H or it could be called X, and so forth. So these are just standard notation that people may find as they go through. You can look all these things up. They are nothing special. It's just a convention that how people call, because these are critical points that you can identify them depending on the crystal structure you have. So that when you say, oh, I'm going to tau to H, then people know that you're drawing from the zone center to the 100 direction. So that's basically it. And you can of course go through, right? You have all these things you can go through. Again, this is a free electron model for FCC and BCC and FCC. Free electron model, you can see all this parabola, interleaving parabola, rather complicated, right? Very complicated, tau to Z and tau to W, and different strategic point. You can also have, and of course this is free electron, you don't have any gap generated. You will have gap generated if you're not talking about free electron. Once you put it inside your solid, you would have this gap. So XUP, hexagonal postback, another rather common crystal structure in transition metal, right? Remember the periodic table that we showed? They are mostly BCC, FCC, and XCP that you will find for transition metal. And so this is one of the common ones. And these are different points that you will see, and this is a free electron energy that you got. Okay, so that's just the appearance of these electronic structure that you may see if you proceed to look for some of these electronic structure. If you happen to meet them, you can find them. Now, how do you calculate some of these things? This band structure. Just very briefly, I'd like to mention some words so that you may hear them in future when people are talking about band structure calculation. There are usually 3 methods called the tight binding methods, Wigner Seitz method, and pseudopotential method. So usually there are 3 of these. I don't want to go too deeply into these discussions because I think if you're a theoretician, you'll be interested in them. But if you are experimentalist, you should be aware of what the nature of these band structure calculations consists of. So qualitatively, so I'll tell you roughly qualitatively what these are. Qualitatively, the tight binding method. Sometimes you hear about this word, and you read your literature, and sometimes some people will say, "Oh, I'm using tight binding method to calculate this structure." Right? Structure, complicated structure like this, you have to have some method to calculate them. And tight binding method really is the equivalent to chemistry, LCAO type approach. You have basis function, and then you make linear combination of these basis functions. And it's good for is quite good for inner electron. What do I mean by inner electron? Electrons that are filling your orbitals. Not very good for conduction electron. Conduction electron meaning that electron to come still, because usually when you say valence band electron,